In this video, we're going to go over section 10.1 from your textbook, which is about the basics of what we call hypothesis testing. What do we even mean when we talk about testing a hypothesis? And then we're also going to go over the specific language and vocabulary that we use in statistics when we're discussing hypothesis tests. So our steps whenever we perform a hypothesis test. Number one, we make a statement regarding a population. So that statement you would say is our hypothesis. Number two, we're going to collect data that might shed some light on the statement's validity. In other words, we're going to try to collect evidence. Step number three, we're going to use math, which we're going to learn in a moment, to determine whether the data collected represents sufficient evidence in favor of your hypothesis. So this word sufficient certainly implies that it's possible to have some evidence in favor of your hypothesis and yet not have enough evidence. And so that's what we're going to see really throughout chapter 10 and throughout chapter 11. It'll be a process of learning all of the math tools that we need to evaluate whether we have sufficient evidence. So here's an example, and this is my hypothesis. I'm going to make this statement about my body weight. I'm going to say my body weight is less than 195 pounds. But you probably know this, that body weight tends to fluctuate. If you weigh yourself, every day, or even if you weigh yourself 2 or 3 times per day, every single time you step on the scale, it's going to be at least a little bit different. So I have a digital scale at home that reads in terms of like 1/10 of a pound, right? And so maybe I step on the scale and I'm 194.4 pounds, and then maybe the next day I'm 196.2 pounds, right? So depending on how much water I've been able to drink and all of these things, your body weight can fluctuate from day to day. But whether you're dehydrated and your body weighs a little bit less, or you're really well hydrated and your body weighs a little bit more, we know that the measurements of my body weight are going to be around some underlying mean, as long as I'm not, really dramatically dieting or really dramatically putting on weight. If I take my measurements for a week, they should all be around some mean. But of course, these are going to be obscured by that random variation we're talking about. So let's say I weigh myself every day for 10 days, and so these are the measurements I'm taking. So this is my data set. You can see that the mean of this data set, my sample mean, is 194.45 pounds. And so this is certainly less than 195 pounds, and so that means that we do in fact have some evidence that my body weight is less than 195 pounds. So I would say that I have some evidence in favor of my hypothesis. Because if my sample mean was greater than 195 pounds, you really wouldn't have very much of a case for your hypothesis. But in my case, my sample mean is less than 195 pounds. But let's take a look at the way I've plotted this data right here. Here, this horizontal line is at 195 pounds. And so you can tell that over the course of the 10 days, the majority of my measurements were below 195. But there were 4 measurements that I took during the 10 days that were above 95 pounds. Again, because my weight sort of varies from day to day. So the question that we want to ask in chapters 10 and 11 is this. Is this enough evidence to conclude in favor of my hypothesis? I mean, having taken these measurements, is there enough evidence here to say that my body weight is less than 995 pounds with some certainty? So here's another way of visualizing this. Over here on the right, this red vertical line represents 195 pounds. okay? This blue vertical line, this represents my sample mean, which is 194.45 pounds. Now, this blue distribution here, this is going to be the distribution of the sample mean. So remember for a moment that whenever you have a random process like this, and you take a sample of size 10, the sample mean itself is going to be a random variable, because if you took 10 different measurements, you would have a different sample mean. So, back in chapter 8, I believe, we discovered that this sample mean is a random variable that, in our case here, would be normally distributed with standard deviation. Well, my standard deviation of my sample mean would be whatever my underlying distribution standard deviation is divided by square root of n. So this blue curve represents the distribution of that random variable. It represents the distribution of my sample mean. And remember, areas under that distribution curve represent probability. And so this area over here, this area that's underneath my distribution curve and lies to the right of 195, this area represents the probability that my hypothesis is wrong. This area represents the probability that I'm actually wrong, and the probability that, the mean is actually going to be greater than 195 pounds. So the larger that area is, the less confidence I have in my hypothesis. And this is a pretty big chunk of the area. So I can't really conclude with very much certainty that my body weight is less than 195 pounds. In other words, there's some evidence for that, but there's really not enough evidence. And again, the reason for this is because this area over here is just too much. It's too big of a chunk of the total area under the curve. So here's a new scenario. Again, my hypothesis is the same. I'm still claiming that my body weight is less than 195 pounds. But let's say I have a new data set where I take 10 measurements and the sample mean is 185 pounds now. And I think we would all agree that this seems to be enough evidence to conclude in favor of my hypothesis, because even if there's some dispersion in my body weight, well, it's probably not 10 pounds worth of dispersion. And so 185 as my mean is certainly less than 195, even given the random variation. And sure enough, when we make the picture here, this vertical blue line represents my sample mean. This curve represents the distribution, the probability distribution of my sample mean, and this red line represents my hypothesis. This is 195 pounds. And so there's really no area at all bound between the x-axis and the curve to the right of 195 pounds. And so we could conclude with practically 100% certainty that my hypothesis would be correct in this case. Okay, so here's another example. So I call my third scenario, where again my hypothesis is the same, but now I've taken a new sample, and actually my sample mean is now again very, very close to 195. Just like in my first scenario, the sample mean is 194.45. But what's different from scenario 1 is that now my sample size is 1,000. In other words, I've taken 1,000 measurements of my body weight. So as my body weight is fluctuating between me drinking water and obviously expelling the water, this is going to capture all of the variation in a very refined way. And so the fact that my sample size is so small, what does that do to the distribution of my sample mean? Well, remember, the distribution of my sample mean is going to have standard deviation which is the standard deviation of the underlying distribution divided by square root n. And this formula indicates to me that as n grows very, very large, then the distribution of my sample mean is going to have very little dispersion. You'd say the standard deviation vanishes as n becomes arbitrarily large. So based on this, again, we can create a picture and notice that my vertical blue line represents my sample mean of 194.45. This vertical red line represents my hypothesis cutoff, where I'm saying this is 195, and my claim is that my body weight should be less than 195. But just the dispersion decreasing in this distribution curve of my sample mean, that allows all of the area under the curve to be safely to the left of that 195 line. So again, practically, I practically have 100% certainty that my body weight is less than 195 pounds, because again, the area under this curve represents probability, and since all the area is to the left of 195, I'd say that I practically 100% of my probability is leaning in favor of my body weight being less than 195. So in this case, we would say there is enough evidence. Okay, so here's some vocabulary. Now that you've got a feel, hopefully, for what we're doing with hypothesis testing, determining whether we have sufficient evidence or insufficient evidence based on the distribution of my sample mean, or in other cases, the sample proportion. Let's go over some vocabulary, because this is going to be important for the rest of the semester here. When I say the null hypothesis, I always mean the baseline assumption. And so I don't mean conservative in the political sense, but I just mean conservative in the sense that you don't want to claim something new and novel. You always want to claim whatever's happening in the baseline unless you have sufficient evidence. So in other words, we're always going to be seeking evidence for what we call the alternative hypothesis. Anytime we do a hypothesis test, we're asking the question, is there sufficient evidence in favor of my alternative hypothesis? So for the null hypothesis, we're going to use this math symbol. We're going to use capital H with subscript 0. And then for the alternative hypothesis, the math symbols we're going to use are either going to be a capital H with a subscript 1 or a capital H with a subscript capital A. And so notice it could really appear any way, but both of these symbols refer to the alternative hypothesis. In a hypothesis test, you always need to have both. You always need to specify what is my null hypothesis and what would be my alternative hypothesis. It's not okay to just have one stated. Go ahead and write out both. These are always going to be converse to each other. And what I mean by the word converse is if the null hypothesis is true, then the alternative hypothesis is false. If the null hypothesis is false, then the alternative hypothesis is true. If the alternative hypothesis is true, then the null is false, and if the alternative is false, then the null is true. That's what I mean by converse. Okay. Here are some examples. So it helps to see examples when you're learning a new concept. And this really goes to illustrate, the most important part of this slide here is to point out what I mean when I say the null hypothesis is our baseline assumption, or when I say the null hypothesis is always our conservative assumption. In the case of a court case going to trial, the null hypothesis, our baseline assumption, is that the defendant is innocent. So you always are innocent until proven guilty, right, in the justice system. And then the alternative hypothesis, what the prosecutors are seeking to find sufficient evidence for, well, the prosecutors are trying to find sufficient evidence to demonstrate that the defendant would be guilty. Okay, so then in a trial where you're trying out, some new medical treatment or some new medicine, perhaps, Well, the baseline assumption when you're going into these clinical trials is that the medicine is unsafe. And if you are a pharmaceutical company that's trying to sell a drug and you have to get FDA approval first, well, the pharmaceutical company is seeking to find sufficient evidence that their medicine is safe. They're trying to collect enough evidence to demonstrate to the FDA that their medicine is safe. Again, in physics, so jumping down to this last one, in physics, modern day physicists, modern day researchers, basically have what you call mathematical models that describe how the universe works, that describe, cosmology, how does gravity work on the large scale, and also particle physics. How does all of the little subatomic particles of the standard model, how do they interact with each other? We have mathematical models to describe this, and what physicists are always trying to do is find new mathematical models that describe the universe with even higher precision. And so when a physicist develops a new model, they then go out and conduct experiments where they collect data, and they analyze the data. And what they're always doing is they're saying, well, my baseline assumption is that our old model is correct, whatever that old model may be. And what you're trying to do with an experiment is provide sufficient evidence or collect sufficient data, to demonstrate with sufficient evidence that the new model is correct. So again, our baseline assumption, is going to be our null hypothesis, and hopefully these examples help you get a feel for how you choose your null hypothesis versus how you choose your alternative hypothesis. Now, when it comes to the conclusion, when you're done with your hypothesis test and you want to state what your conclusion is, we never say that the null hypothesis is true. We never say that we accept the null hypothesis, and we never actually say the defendant is innocent. And this is actually a really, really, really interesting take, because what we say instead in the United States judicial system is we say that the defendant is not guilty, right? I'm sure you've heard this before too on court shows. But a ruling of not guilty is not the same as an innocent ruling. The jury is not concluding that the defendant is for sure an innocent person. The jury is only concluding that there wasn't enough evidence to conclude that the defendant was guilty. So we never say the defendant is innocent, for example. Instead, the phrases we would use in the language of statistical hypothesis testing are these. We would say, well, there's not enough evidence to reject our baseline assumption. We might say that we fail to reject the null hypothesis. And we would say again that the defendant is not guilty. So this is really important. This is something you should internalize. This is something that you will be, tested over on an exam. Is like, do you understand the difference here? We're not actually proving the null hypothesis. We're just saying that we don't have enough evidence to reject the null hypothesis. So I've already alluded to this a little bit, but you can make an error in the courtroom, right? In a criminal trial, there's two cases for the reality of the situation. The reality is that either the defendant is innocent or the defendant is guilty. And that's what is true about reality before the trial even begins. After the trial is over, the jury has ruled that the defendant is either guilty or not guilty. And so there's 4 possible outcomes that I can represent in this table. When a defendant is innocent and they are ruled not guilty, we would say that the jury comes to the correct conclusion. When the defendant is guilty of the crime and the jury rules that the defendant is guilty, we would also say that the jury comes to the correct conclusion. Now, this is an important vocabulary, or 2 important vocabulary terms in statistics. if the defendant were innocent and the jury rules that they are guilty, this is what we call a type 1 error. In other words, when your null hypothesis is true and by mistake you have determined that the alternative hypothesis is true, that's what we call a type 1 error. You incorrectly side in favor of the alternative hypothesis. Okay, so then when the defendant is truly guilty of the crime and the jury concludes that they are not guilty, this is what we call a type 2 error. Again, using different language to mean the same things. If the alternative hypothesis is true, and you conclude in favor of the null hypothesis, that's what we call a type 2 error. And so, I sort of said this out loud a second ago on the previous slide, but there's a nice analogy between the courtroom and how we formally talk about errors in statistics. If your null hypothesis is true and you choose to not reject the null hypothesis, then this would be the correct conclusion. And if your alternative hypothesis is true and you do reject the null hypothesis, this would also be the correct conclusion to arrive at. But if the null is true and then you end up rejecting the null hypothesis, this is a type 1 error. And if the alternative hypothesis is true, but you fail to reject the null hypothesis, that would be a type 2 error. So notice the analogy here. I might also speak casually in the upcoming lecture videos about these facts, right? So if my null is true and we choose not to reject the null hypothesis, we would call this a true negative, especially when we talk about in medicine, whenever you are trying to diagnose a patient and you're testing them for disease, choosing not to reject the null hypothesis would be like a negative test, right? So the null hypothesis is that the patient does not have a particular disease. The alternative hypothesis would be to say, yes, this patient has a particular disease, right? So just to throw something out there. A null hypothesis would be to assume your patient is healthy. Maybe the alternative hypothesis for a specific leukemia test, well, the alternative hypothesis would be that the patient has leukemia. So anyways, if the patient is healthy and you don't reject your null hypothesis, that would be a true negative test. If the alternative is true, if your patient truly does have leukemia and you choose to reject the null hypothesis, that would also be a true positive. You would have a positive test result and that test result would be true. But again, you can fill in this table here. If the patient is leukemia and you fail to reject the null hypothesis, that would be a negative test result, but it would be a false negative. If the patient is healthy, but you failed to reject the null hypothesis, well, that would be a positive test result, but it would be a false positive, because in reality, the patient is healthy. So make sure you understand these three tables and how they relate to each other before we move on. The way we talk about errors in the courtroom, the way we talk about errors formally in statistics, and the way that you might casually talk about errors, like in a medical setting. And the last little bit that we're going to tie this all together with is that when we talk about the probability that we will reject the null hypothesis when the null hypothesis is true, we're talking about the probability of making a type 1 error. Remember, rejecting the null hypothesis when the null hypothesis is true, that was a type 1 error. And we have a symbol to use whenever we're talking about the probability of a type 1 error. And the probability of a type 1 error is going to be represented by alpha. And we're going to call alpha the level of significance. So one more vocabulary term from a section in your textbook that's very heavy with new vocabulary terms is the probability of a type 1 error is called the level of significance, and we represent it with the Greek letter lowercase alpha. Now, the probability that we will not reject the null hypothesis when the alternative hypothesis is true, well, that's just the probability of a type 2 error, right? So when we say that the alternative hypothesis is true, but we do not reject the null hypothesis, that would be a type 2 error. So this probability is the probability of a type 2 error, and we represent it in symbol with a Greek letter lowercase beta. So what's the probability that we will not reject the null when the null hypothesis is true? So this is a good thing. That probability would be 1 minus alpha. And the probability that we will reject the null hypothesis when the alternative hypothesis is true, that's what we call the power of a hypothesis test. And the formula for power is going to be 1 minus beta, where we defined alpha and beta the way we do on this previous slide. So these are the probabilities that we are wrong in different ways. And these would be the probabilities that we are actually correct in 2 different ways, right? And ideally, we would love to have a hypothesis test that has a very, very low level of significance. We want the level of significance to be very low in a hypothesis test because we want the probability of making any error to be very small. On the other hand, we want the power to be very high because if our alternative hypothesis is true, then we want to be able to reject the null hypothesis as often as possible. So we want the power to be high. We want the level of significance to be low. And whenever the level of significance is very low, that then means that 1 minus alpha is very high. And so there's a high probability that we won't reject the null when the null is true. That's a good thing. And likewise, when the power is very high, and that means beta has to be very low. So the probability of making a type 2 error would be low when the power is high. So remember, vocabulary-wise, we want the power of the test to be high. We want the level of significance to be low. So again, putting this back into my table that I used earlier, but now we're talking about probabilities. The probability that your null hypothesis is true and you do not reject the null is 1 minus alpha. The probability that null is true, but you reject the null hypothesis is called alpha, and we call that the level of significance. The probability that your alternative hypothesis is true and you don't reject the null, that's beta. And the probability that your alternative hypothesis is true and you, in fact, reject the null hypothesis, that would be calculated 1 minus beta, and that's what we call the power. So again, keep these tables in your head and memorize them and be able to just reproduce them very quickly on an exam because this is going to be important in keeping all of the details of hypothesis testing straight in your head. All right, so thanks, and I'll see you in the video for 10.2.